you're our last speaker of the day. You're also from KICP in Chicago, and your talk is about the probing gravitational waves couplings in dark energy theories. So please, William, go ahead.
Thank you. Yeah, I just wanted to thank everyone for listening to my talk and for inviting me to come speak at this cosmology and gravitation workshop. As the title says, my talk is called Probing Gravitational Couplings in Dark Energy Theories. This talk will be related to the one that Macarena just gave us. And so we're all familiar with the standard lambda CDM model and how it's been incredibly successful at helping us describe the constituents that our universe is made of. But lots of unanswered questions have led to us to develop extensions of the lambda CDM model, in particular dark energy theories. And there's a lot of different ways of doing this. Macarena talked about some of them. You can have scalar, vector, biometric theories of gravity. And the main thing here is that you're promoting lambda to some type of dynamical field that's going to source the accelerated expansion of the universe. So I'm going to be, and these types of theories are going to lead to a wide variety of potential observations in the gravitational wave sector. So, for example, we heard about how it can change the amplitude or the speed of propagation. And I'm going to dive a little bit more into a feature of these dark energy theories that would lead to a change in the amplitude of gravitational waves. So in particular, I'm going to talk about how there's a lot of dark energy and modified gravity theories that lead to a time variation of the gravitational coupling G, and this can be probed with standard siren experiments like LISA. So just as an overview, I'm going to just quickly hit on that again, and then I'm going to go into how it's important for us to define the actual gravitational couplings that we're working with, because once we move away from Einstein's theory of general relativity and into some of these extensions, and extensions in these dark energy and modified gravity models, it turns out that we can actually have a number of different gravitational couplings. And these gravitational couplings can depend on the types of environments we're in, as well as the types of interactions we're considering. And it's really important to define these because this can offer important information on whether or not a particular model is viable when considering constraints on this parameter that have already been performed, as well as the outlook for future experiments that'll test things like this, such as LISA. And then finally, we'll go in and we'll explore lunar laser ranging and binary pulsar constraints with a more agnostic attitude about the types of gravitational couplings that are that might show up in theories of modified gravity. So to begin with, I've written down a generic action that describes the propagation of metric perturbations or gravitational waves. So here we have, in a FRW background, here we have our scale factor, here we have our gravitational waves, and then here we have a gravitational coupling that is allowed to vary in time. So this leads to an equation of motion that we are pretty much familiar with. So we have the Hubble rate h, we have the amplitude of our gravitational waves, and we have this additional alpha m parameter that Macarena mentioned in her talk. And this particular parameter is something that shows up when our dark energy or modified gravity theory involves a variation of the gravitational coupling. And it's given by the time derivative of g divided by g times the Hubble rate. And as we saw before, this in standard Einstein theory, this term vanishes. But in these additional models, in these extensions, this is going to be a friction term that's going to affect the amplitude of the gravitational wave signal. And this is going to lead to a different luminosity distance that would be able to be probed with multi-messenger standard siren tests, like, and LISA is the great example of that. And so we can write down the relationship between the gravitational wave luminosity distance, which is inferred from the amplitude of the gravitational wave, with the standard electromagnetic luminosity distance. And that gives us an equation that can relate the gravitational coupling at the redshift and position in which it was emitted versus, or in the position where it was emitted versus the observers. But yeah, so I was talking about how a lot of gravitational theories can be screened, and that means that the interaction is going to depend on the density of the environment you're in. So for example, if you have a source for gravitational waves that emits them, and they propagate to us over cosmological distances, they can leave the screened region, enter a transition zone, and they can do all sorts of things during this propagation. But once they get back to us, they'll enter a screened region, so a similar dense solar system environment. And in this figure, and it's written in terms of the Planck mass, but in this figure, it just returns to the same value it was before. And effectively, what this would be portraying is us measuring the local value of the gravitational coupling in a screened region. Now, this isn't the only scenario. This is just saying that when we actually measure these gravitational waves, we're measuring the local value of the gravitational coupling. However, what we're talking about here, this can in principle vary with time. And so we would in principle be able to, if there's a time variation of the local coupling, we would in principle be able to measure that as observers. Now, you might be wondering, hasn't a time varying G already been measured? And the answer to that is yes. So it's been done a number of different ways. Probably the two most well-known examples are lunar laser ranging and binary pulsar constraints. And those have already found that the time variation of G divided by the coupling itself, they place a bound on it that is 10 to the minus 3 times the Hubble rate. So this is really important because LISA is projected to be sensitive enough to constrain this parameter at 10 to the minus 2 times the Hubble rate. And so if this is the case, what can LISA really tell us about this particular feature of dark energy and modified gravity theories, considering that there's already a constraint that's probably going to be better than it? And the answer is, if we're not careful about how we define our gravitational couplings in these theories, LISA might not be able to give us information on this particular parameter.
Sorry, William, Shunchan has a question for you.
Yes.
Can you briefly explain why this lunar laser ranging experiment can constrain this time variation of G at such a highly sensitive level? This is a super sensitive when compared. I mean, this is the right hand side is the current Hubble constant, which is super tiny.
Yeah, that's an interesting question. I don't know if I could offer an exact answer on why exactly lunar laser ranging is so sensitive to this. But yeah, it consistently offers the best constraints on this parameter. It's basically sending signals to the moon that are reflected back to us. That allows some very precise measurements of the distance to the moon and allows us to probe the gravitational interaction there to a very high level of precision. But you're right, it is very precise.
Okay, thank you.
Yeah. But with this though, so I was talking about how it's very important for us to consider the exact gravitational coupling we're considering in our theory when we go beyond Einstein. And it turns out that the gravitational couplings actually depend on the environment we're in and the types of interactions we're considering. So for the rest of this talk, I'm going to define two different gravitational couplings that can arise when we go beyond general relativity. So a solar system test like lunar laser ranging, that's going to probe the matter-matter interaction GN. And we're going to call it GN for the rest of this talk, and that's going to be the gravitational interaction between two massive bodies. And then we also have the gravitational self-interaction, GGW. And this is going to be the gravitational interaction that something like a standard siren test like LISA would be sensitive to when probing the gravitational wave luminosity distance. So if you haven't heard this before, it might seem a little strange that there can be different gravitational couplings because we're just so familiar with it just being G. And in order to illustrate how these different couplings have arisen, I have provided an example here of chameleon gravity. So here what we see is a generic action for a chameleon theory of gravity. Here I've defined GP as the typical G that we think of when talking about Newton or Einstein. And then we have these additional functions. So we have this a squared that's a function of the field that's directly coupled to the metric. And then we have these other functions of the field that define our theory of gravity. So their exact functional forms won't be important for this discussion, but some of the generic features will be. So, for example, if we are trying to find the gravitational interaction in the Earth-Moon system, we would find GN by taking the non-relativistic limit of the theory and calculating the force of gravity in this case. And so what has been found is that these masses interact with the chameleon field, and that's going to give them an additional scalar charge that is going to depend on the density and the environment. So this has been calculated before, and it's been found that this GN gravitational coupling is approximately equal to GP, so that's the Newtonian G, and A squared, which is the coupling to the metric of the scalar field, plus this additional contribution. So here beta is a model-dependent parameter. Q1 and Q2 are the effective scalar charges that come about when the masses are interacting with this additional scalar field. So moving on to the self-interaction coupling GGW. In order to find this, this is the standard calculation when getting the linearized Einstein equations. So what you basically do is you consider perturbations of the metric and you identify GGW with the coefficient multiplying the equation of motion for the propagation of your gravitational waves. And this is simply given by GP times A squared, which again is the coupling of the scalar field to the metric. And so just by looking at these, you can see that we have different gravitational couplings, and that's because these masses have an additional interaction with the chameleon field. So in principle, these gravitational couplings are different, and because they're different, we have to be careful with how we treat them, and we wouldn't necessarily expect their time evolutions to be the same either. So for the rest of this talk, we're gonna consider these as different couplings, and we're gonna be agnostic about their potential time evolutions. So binary pulsars are an interesting potential probe of this because the lunar laser ranging, that's going to be sensitive to GN, whereas the standard siren tests are going to be sensitive to GGW. And so binary pulsars are a potentially interesting probe of this because they're going to involve both of these gravitational couplings. So in a typical binary pulsar test, how we measure this is we measure the decay of the orbital period of the system. And this is going to involve GGW because that's going to govern the production of gravitational radiation that's going to contribute to the decay of the period. it's also going to involve GN because you have two massive bodies that are orbiting in a gravitational interaction, and if that's varying with time, that will affect our orbital period as well. So what we're going to do here is we're going to actually remain agnostic about these gravitational couplings and see if binary pulsar constraints offer anything informative about probing the time variation of these couplings. So typically how we would do this is we would consider the solutions to the linearized Einstein field equations. So we're gonna perturb our metric, and we're gonna get GGW, which again is that gravitational interaction that multiplies the metric, and then we're also going to have our perform an expansion on our stress energy content, and to leading order, that's going to give us the second derivative of the quadrupole moment, where the quadrupole moment is given by a system of point masses. So following the standard procedure while allowing GGW to vary with time, this is going to result in the following changes to the standard GR power formula. So here is the term that we're all familiar with. So the only difference is we've defined this as GGW, and it's going to depend on the third time derivative of the quadrupole moment. The brackets denote time averages. However, we're also going to have these secondary contributions that come from the time variation of this gravitational coupling, as well as different combinations of these quadrupole time derivatives. And so in order to quantify these effects, what we're going to do is we're going to calculate each one of these terms and see what happens. So in order to calculate each one of those terms, we have to evaluate the derivatives of the time derivatives of the quadrupole moment. And we have to remember that we're allowing time variations in GN. So that's also there's going to be additional factors of dot GN that are going to come out of these calculations. And then beyond that, we just assume a Kepler orbit, and we calculate everything and take the time averages to find the new formula for GR power. And to leading order, you're going to have the same term you would expect from GR. And then the next two leading order terms are going to be quadratic in the time derivatives of these gravitational couplings, and then where these K1 and K2 terms are just functions of the eccentricity that are roughly order 1. So just by looking at this, you can just read off from this equation and expect that these terms are going to be pretty small because they're quadratic in these time derivatives. Now we're going to estimate the size of all these terms, but right off the bat, we expect these to be pretty small. So now to fully evaluate this, we need to consider some of the other effects. So we relate the power loss to the decay of the period in the standard way, and the leading order term from GR for this period decay is going to be given by this famous formula, which when these couplings are the same, reduces to the standard formula in GR. And so we also note that this ratio is changing in time. And so because this ratio is changing in time, slowly varying in time, we have to estimate the effects of this change with a Taylor expansion, which is given below. And so what we see when performing this Taylor expansion is that we're going to get additional terms from this leading order 1 that are linear in these time derivatives. So there's going to be that additional contribution, and then the next contribution is going to come from the period decay that would be associated with the normal orbital motion that is that is just going to result from the varying matter-matter interaction. And this was found a while ago, and this is actually how binary pulsars have previously been used to constrain the time variation of G, just by noting these effects. And so what we see here is that the total period decay is going to be given by all of the contributions from gravitational radiation, as well as these orbital motion, as well as these orbital motion effects. So what we can do is we can actually use Hulse-Taylor binary data, and we can estimate the size of all of these contributions to the period decay. And so the Hulse-Taylor data, that's going to give us our period, masses, eccentricities, etc. And so we can plug those in to estimate the sizes of those terms. And then also what we can do is we can use the lunar laser ranging constraint on GN here and plug that in. And then for GGW, we can we're just going to assume that it can vary at the Hubble rate, just because there are some theories of modified gravity that suggest that this would be the time variation you would expect. So we can plug all those results in, and what we find is that we have our leading order effect, and then we have this secondary 10 to the minus 4 deviation that's going to come from this De Moore paper in 1991, which is going to be the orbital motion of GN. And then the next leading order effect is 10 to the minus 10, which comes from the Taylor expansion on the previous slide, and this one is related to the time variation of GGW. And then we have a bunch of other way smaller effects, so those will be the ones that were quadratic in the time derivatives. And this is really interesting because at best, the binary pulsar data can detect deviations from GR of order 10 to the minus 3. And so what that basically means is that in order to offer a meaningful probe of the time variation of GGW, binary pulsar data would have to be more sensitive by order of magnitude of like roughly 10 to the 6 or 10 to the 7. So what we see here is that despite binary pulsar systems being sensitive to both of these couplings, binary pulsars do not provide a good constraint on GGW because the decay of the period, additional effects would be dominated by GN. And so in conclusion, what we see here is that in dark energy and modified gravity theories, these are going to generically result in different gravitational couplings. And this is really important to consider because once we move away from Einstein theory, these couplings can have different forms, and in principle, they can have different time evolutions. And what we've seen so far is that the matter-matter coupling GN, that's been very tightly constrained with lunar laser ranging experiments, but we don't yet have a good constraint on GGW. And this is very interesting because if you have a modified gravity theory that predicts different time evolutions for these parameters, we don't have a good constraint on GGW yet. And so this leads to the conclusion that upcoming probes like LISA they're gonna offer a novel look or novel probe into the nature of dark energy because they're going to be sensitive to the time evolution of this parameter, which is a generic feature in these sorts of modified gravity theories. Just want to say thank you for listening to my talk, and I am open to any questions.
Thank you, William. So we have a question.
Okay.
So first, I guess Danilo was first, and then John Massimo. Yeah.
Hi, thanks for your talk. I have a question, which is maybe a bit silly, but could this self-interaction coupling make GR renormalizable somehow? And maybe you could have some constraint on this GW in order GR to be renormalizable?
You know, I have not considered that. I'm actually, I'm not sure if that would have any implications for renormalization. That's an interesting question, though.
Okay, thank you.
Can I add a comment to that?
Oh, please.
Sure, sure.
So there can be different reasons why you get time variations of gravitational couplings. And in our specific way, it's something that just comes from interactions with this additional dark energy field. It's not like the usual kind of running of couplings that you consider in UV theories. So this is something that it just only appears as a net effect when taking considerations of couplings with additional fields that have a non-trivial evolution in these dense environments. So just one example is this chameleon model. So this is within the Horndeski theory. So these are as renormalizable or non-renormalizable as GR. So these are the kind of theories that we're looking at instead of a kind of fundamental time variation of the actual coupling. Because in that case, then there are other constraints, for example, from the early universe that you would also expect to have in this case. The time variation of this G only comes through because of the interactions with dark energy that are only relevant at late times.
Okay, I see. Thank you.
John Massimo, if you'd like to.
Yes. I have a question about you said that you consider Keplerian orbits for your calculation, while people in GR or for considering the emission gravitational waves from binary pulsars go much beyond. I mean, they consider GR effects, they go beyond Keplerian orbits. I was wondering whether there can be, what is the effect of whether there can be degeneracies between relativistic effects and the kind of calculations that you are considering, and also the role of screening on what you are doing.
Yeah, so we considered Kepler orbits because that's just going to be the simplest realistic case. That's also a reasonably good description of a lot of systems, and so we were doing this with the idea of actually using the Halls-Taylor binary data to kind of estimate these second order effects. I don't believe that. I think Kepler orbits are probably a pretty good approximation here because these other terms are so small. We didn't look at other types of orbits, so I don't know exactly how that would impact this analysis. But Kepler orbits are, especially when using that type of data, those are a pretty good approximation.
But the Damour effect, that's a relativistic effect that comes from the orbit, right?
Yes.
So that's the only relativistic effect that we consider that is the leading one. And all other effects in principle from the orbit would bring additional terms on time variations of Gn, but not of GGW, which is what we're interested in trying to constrain here.
Yeah, so I guess if anything, that would weaken the potential constraints on GGW.
Okay. Thanks.
Any more questions? No, so let's thank William again. And also thank all the speakers of this afternoon session.